back, and we're going to be learning some Haskell today. I had such a hard time basically getting this whole thing set up again. I haven't streamed in a while, so like my OBS wasn't working right, and OBS wasn't working right, and then I tried to get NixOS sort of like updated, and then that ended up just crashing for some reason. Had to fix that. And finally, we're here, but it means that I don't have that much time before choir starts. So we're going to do a little bit today. It's better than doing nothing, I think. And we will, so what we'll do is, okay, so I've been struggling, like, what do I want to do? The last week has been really low motivation. I, quit my job, and so like that took some processing, in general. And then while I'm processing that, I was like just really low energy. It's kind of like, what's my future? What do I want to do? Um and now I'm finally getting motivation back and wanting to do stuff. So, I was like, do I want to my main language is Elixir, right? So, but it's like one of the things I rarely ever actually like stream because I don't want to stream like learning Elixir because I kind of know it and I'm selfish and I want to learn something new all the time. So, we did some Erlang and I don't want to give up on that, but I've always had like a soft spot for Haskell. I tried learning it before. I wouldn't say that I got through it. Um, so this time, let's try to get, through this book. It's called Learn You a Haskell for Great Good. Yeah. Hey there. Yeah, so I really want to get through it. I feel like when people who know Haskell are talking, I'm always like, what the hell are they talking about? It sounds so cool, so I just want to know it. Um, so there we are. So I have about an hour. So let's see how much we can get through. We're using this book, Learn You a Haskell for Great Good, and we'll just kind of go through it. You know, um, I think last time when I was learning this, I got stuck. I don't know where I got stuck. It was just kind of like the book just sort of took a turn and it was just got really like, here's just a library. Here's just a whole lot of libraries. And I was like, well, what am I supposed to do with this? Am I supposed to just play with a library? So I didn't know what to do. Um, so this time we're just going to stick through it. This is my goal. It's like losing weight. I want to lose a little bit of weight and learn some Haskell. All right, here we go. I got GHC running, Glasgow Haskell compiler, I assume. So you can do that too if you want to do any of these things with me later. And we're running 9.10.3. This is 9.2.4. And this is kind of like all stuff that you would kind of expect with any REPL, like adding numbers together. I assume that's a little slow. 10 divided by 2, and then 10 divided by 3. Okay, so it gives us floating points. We can use parentheses. That makes sense. All right, I remember Haskell has funny things with negative numbers. Um, so if we do 5 times -3, it says, what the hell is this? But doing 5 times -3 is fine, with parentheses around the -3. It probably just doesn't want to apply the minus operator there. Boolean algebra, pretty straightforward, so we just have to remember that it's called true and false. Glorious Haskell compiler, nice. Okay, so far so good. Oh, it's like, okay, this should still be true. Okay, equality is equal equal. And then we have our not equal. Okay. And strings are in double quotes. What about doing 5 plus? Yeah, so this probably won't work, right? No instance of num string arising from plus. So probably it wants to turn this to a number. If we try to do true equals 5, it would tell us the types don't match. You can't compare apples and oranges. Okay. You can do integer and floating point because 5 can act like an integer or a floating point, but 4.0 can't act like an integer. So the 5 changes. We've been using functions. Asterisk star is a function that takes two numbers and multiplies them, and it's infix. Most functions that aren't used with numbers are prefix. Yeah. Functions are usually prefix, blah, blah, blah. So succ for successor gives us the next thing. Okay, it only works with numbers. Probably not with floating points. Oh, it does add 1. There's min and max. I believe it. Oh. Oh, it only takes 2 numbers. Okay. Function application, putting a space after it, then typing out the parameters has the highest precedence. So this is going to have the highest precedence. So we can do max 10 and 1. That'll be 10 minus min 10 and 1. So this should give us 9, right? Yeah. I see. So if we want to get the successor of the product of the numbers 9 and 10, we couldn't write successor 9 times 10. Right, that's fine. Div takes 2 integers, and if you want to call something infix that takes 2 parameters, you put the backticks in it. So I assume this can work with max also. Yeah. Dividing 10 by 2 gives us 5, and by 3 gives us 3. Okay, so this is integer division. Parentheses. It's just telling us you don't need parentheses, I think. All right, that was the first section, right? Yeah, first functions now. So we're going to make a function, double me, and then it takes in a parameter, and then we do this, x times x. I guess we can just do x just to be contrary. We can do x times 2, right? Now we do double me 10, and we get 20. Great. There's equal. Save this as baby.hs. I think I've done that already. So let's make a new file. What? HS, right? Okay. Double me x is equal to 2x, 2 times x. So we save that, and now we can load the file. Okay. And now I can do double me 100. Great. That worked. Does our thing work? Yeah, it works on floating point numbers too. Double us. So this doubles each and then adds them. Let's make a function that takes two numbers, multiplies by 2. All right, so we'll do that. And it was called double us, and we need 2 parameters now. So we just call double me x plus double me y, right? Seems correct. And now we run GHCI. We load chapter 1, and we call double us with 2 and 3. So that's 4, 6, 10. Works. Yeah, we already did that. We snuck ahead. Elixir Conf is coming up. I want to submit a talk, but I have like nothing to talk about. I'm sure I do. I just don't know what. I think it's in May in Spain, Malaga, Spain. So, doing a little advertising for them. Functions in Haskell don't have to be any in particular order. You can define, okay, so it doesn't matter. Now we're going to make a okay, let's not look at it. Now we're going to make a function that multiplies a number by 2, but only if that number is smaller than or equal to 100, because numbers bigger than 100 are... Okay, so it's like multiplies a number. So it only doubles if it's 100 or less, right? Okay, cool. So we'll call this double small, I guess. And there's probably something like, I know there's an if x is less than or equal to 100. I'm guessing now. Maybe there's a then. God, doesn't feel very Haskell-y. Then double me x else x. Well, so far it doesn't give me any error. Let's see. Huh. Well, yeah, same thing, right? Um, so I guess it kind of looks like maybe that is kind of better formatting. I'm gonna have to figure out what the style is for this stuff. Oh, this language processor doesn't feel very good. Okay. I don't know. Right here we introduced if statement, blah blah blah. I don't know what any of this is saying. It's just saying everything's an expression, I think. Else is mandatory. If we want to add 1 to every number that's produced in our previous function, we could have written it like this. Oh, it needs the parentheses, right? That makes sense. Notice the tick at the end of the function name. It's like prime, I guess. So it's kind of saying like, hey, this one's another version of it. Because tick is a valid character in functions, we can make a function like Conan O'Brien equal it's a me Conan O'Brien. It's kind of like a funny function. It's a function that returns this expression. Takes no parameters, I guess. Um, Functions can't begin with uppercase letters. This function takes no parameters. When it takes no parameters, we usually say it's a name or definition. So, oh, is that we can't change things? Huh. All right, so that we've done 2 parts. We're ripping through this, guys. We're going to make lists. Lists look like okay, so they're homogeneous. They all have to be the same thing. So you can't have a list that is like, well, let me make sure I can make a list. And then I can't make a list that's like this. Yeah. But I can make a list like this. Yeah. And I assume I can mix integers and floating points because the integers will become floating points. Yep. Here they're mixing it up and that won't work. Strings are just lists of characters. Hello is just, okay, so a character is like this. And then so, does that mean this is equal to this? Huh. Oh, it's a list of characters. There we go. Hey, we learned something. All right, cool. A common task is putting 2 lists together, and that's just done with plus plus. So here's one list. Here's another list. That makes foo. Okay. Watch out when using plus plus or concat operator on long strings. When you put together 2 strings, it has to walk through all of them. So they're basically linked lists. It's not going to just sort of copy memory. It's going to like go through all of them and make lists. Putting something in the beginning of the list is fast. So if we have the beginning of a list, we put here, we just want to put an element, right? So if we want to put F in front of this list, that works. And that's basically saying like adding 1, 2, 2, and 3. Because it has a pointer to the first element. And if you want to just insert it, it just like basically changes where that pointer is pointing to. It puts that new element in there and changes where that element's pointing to. So it's a constant order of operation there. I mean, like the first thing doesn't have to be a list. We can put a list inside of a list, I'm sure, you know? Oh, oh, right, because these need to be lists then. Otherwise, they're not. Because it needs to be homogeneous. They all have to be lists, right? Makes sense. Um, whoa, okay. Empty list and a list containing the empty list and a list containing 3 empty lists are all 3 different things. Yeah, I think we just said it. If you want to get an element out of a list by index, use the bang bang operator or function. So if I have 1, 2, 3, and I want to get the second one out, excuse me, bang bang, that gives me the last one. So this is indexed by 0, right? This gives me 2. Okay. And then we have A, B, C. This will give me B. All right. Lists can contain all other lists. Yeah, we already did that. But I mean, just like we had this, like if I make a list and then I try to put a list of numbers in here, I assume it's going to fail. Yeah, it needs to be the same kind of item in the list. They can all be different lengths, but they have to be the same type. So you can compare lists if the things they contain can be compared. So 2 lists are the same if all their elements are the same. I guess, you know, I don't really care about this. All right, we have head, which will give us the first item in a list. Head, in the use of head, this is a partial function. It throws error on many lists. Use pattern matching. Oh, so it did give me the answer. It just it's just telling me that it's a partial function and throws error on empty list. Okay, so it's not best practice. It's kind of funny to say that for head. And tail should give me 2, 3. It's just going to remove the head here, and I get 2, 3. There must be some way, I guess, like I can run it with this. Is that right? Nope. There must be some way to tell to not do that, but worry about it later. And then last, if I give it a long thing, it's going to give me the last one, 4. But this is also going to be slow, I'm sure, because it has to go through all of the elements. And it takes a list and returns everything except its last element. So it's kind of like 1, 2, 3. What happens if we try to get the head of an empty list? This is what this whole error was, right? Like head empty list, and it's like, ah, you fucker, you didn't listen to me. Can't do that. Oh my, it blows up. It doesn't have a head. When using head, tail, last in it, be careful not to use them on empty lists. This error cannot be caught at compile time, so it's always good to take precautions, yes, by using these other pattern matching and things. Length takes a list and returns its length, obviously. Okay, this should be 4. Whoops. Null checks if a list is empty. Okay, so this will tell me if this should be true and this should be false. Reverse reverses a list. Take, I assume take gives me the first n number of them. So we'll say 3 out of 1, 1, 1, 1, 1, 1, 1, and I'll have just 3 1, 1, 1s. Drop will drop the initial 3, which will give me 3 more. I'm giving you guys terrible examples, by the way. Hopefully this makes sense, right? Like you can see that it gives you the last 3. And here it's saying if I try to drop too many, more than it has, then it's just going to give me the empty list. Maximum takes a list of stuff that can be put in some kind of order and returns the biggest element. So we have max, but maximum, it works on lists. And this should give me 20, right? Sum takes a list and a list of numbers and returns their sum. So summation would be like, here we get 6. Product takes the list and returns their product. Ooh. $24. Element takes a thing and a list of things and tell us if that thing is an element. So it's going to return us true or false. So we say like, is 10 an element of 1, 2, 3? And it'll say no. And then if I add a 10 in here, it's true. We have some more time. Oh yeah, we have plenty of time. Texas ranges. Like Texas, like shooting, Texas, like shooting ranges, Texas, where the Wild West, where people used to shoot. I guess people still shoot. What if we want a list of all numbers between 1 and 20? Sure, we could type them all out, but obviously that's not a solution for gentlemen who demand excellence from their programming language. Instead, we'll use ranges. I remember like I was doing some TypeScript programming and I was like looking for some like thing to give me a range, and it was like kind of like just annoying. Like I think you can use array or something, but it had limitations. It wasn't as flexible. Really annoying. Ranges are a way of making lists that are arithmetic sequences and of elements that can be enumerated. Numbers can be enumerated 1, 2, 3, 4, etc. Characters can also be enumerated. The alphabet is an enumeration of characters from A to Z. Names can't be enumerated. What comes after John? I don't know. J- j- to to make a list containing all the natural numbers from 1 to 10, you just write 1 to 20. All right, easy, right? And we can do that for characters. B to, let's say, E. And if I do A, it's not happy. Oh, it just says it's empty. All right. Empty list, which comes out as an empty string. Except that writing out long enumeration sequences manually is stupid. This is very like negative language. Shame on them. I wonder if the letters actually wrap, right? Because can I do this? No. Or this? Aha. So it's using the ASCII chart for this. Something. Um, what if we want all even numbers? So we start with like 1, 3. I wonder if I can just do this, right? Doesn't like it. Okay, so you got to give it two numbers and then where it ends, and then it continues it. And the same thing would be 1, 2. And it's going to say it can't do this. Oh, oh, 1, 2. Right, of course. 2, 4. Oh, it just like stops at 20 because it's the last one. That's cool. Right. So I tried to do this. It doesn't let you. Oh, right. This one is trying to do powers. That doesn't work. 20 to 1, you can't do 21. You need to give it us two numbers to start with and then where it ends. Okay? Watch out when using floating point numbers and ranges because they are not completely precise. Their use in ranges can yield some pretty funky results. 0 0.1, 0 0.3, dot dot, to 1. Yeah. Well, funky results, but at least it's deterministic here. You can also use ranges to make infinite lists by just not specifying an upper limit. Later, we'll go into more detail on infinite lists. For now, let's examine how you would get the first 24 multiples of 13. Sure, you could do 13, 26, and then 24 times 13, but there's a better way. Take 24, 13, 26, dot, dot. So I assume I'm not going to get in trouble if it'll just give me a, oh shit. All right, so I'll say this is my list, and then I can do take 24 from L. There we go. So they both work. So I guess when I type it in like directly here, this is saying it needs to evaluate it right now, so it's going to give it to me. But when I do this, it's saying I don't really need to evaluate it. So it's just doing that lazy evaluation thing at this point. I'm sure we'll go into that soon. Sorry, hold on 1 second. All right. A handful of functions that produce infinite lists. So cycle probably gives you a circle here. Yeah, it's just gonna go back and forth. Um, take 12 is gonna give you the first 12 characters of this cycle. I don't think I need to try that. Repeat is going to take an element and just make the same thing forever. So if I do L equals repeat, then I do take 100L, I just get a whole bunch of ahs. Although it's simpler to just use the replicate function if you want some number of the same element in a list. Replicate 310 returns you 10, 10, 10. Uh, all right, list comprehension. This seems like maybe a good place to stop after we're done with this. Why is there Kermit here? Like, why? What's Kermit have to do with the list comprehension? I'm missing something. If you've ever taken a course in mathematics, you've probably run into set comprehensions. They're normally used for building more specific sets out of general sets. A basic comprehension for a set that contains the first 10 even natural numbers is s is equal to 2x, where x is a natural number and x is less than or equal to 10. The part before the pipe is called the output function. X is the variable, n is the input set, and x is less than or equal to 10 is the predicate. That means that the set contains the doubles of all natural numbers that satisfy the predicate. If we wanted that, we could do something like take 10, where we just like make an infinite list 2, 4, and on and on. But what if we didn't want doubles of the first 10 natural numbers, but some kind of more complex function applied on them? We could use a list comprehension for that. List comprehensions are very similar to set comprehensions. We'll stick to getting the first 10 even numbers for now. The list comprehension we could use is x times 2, where x is 1 to 10. All right, let's just write that. X times 2, where x is less than or equal to 10. Was that it? Damn it. Shit. Oh, you got to use the assignment. So this is going to make it, oh, we're going to only limit it to 1 to 10. Duh. Um, I see. Here's the condition that we can add. Let's add a condition to that comprehension. Predicates go after the binding. Let's say we want only elements which doubled are greater than equal to 12. So we say where x times 2, when we double it, it's greater than or equal to 12. So we'll only get 12, 14, 16, 18, 20. Okay. How about if we wanted, numbers from 50 to 100 whose remainder when divided by, is there like a remainder? Okay. So we want, let's just make the x first. 50 to 100. When the remainder divided, whose remainder when divided with the number 7 is 3. So we made, this is the set that we're assigning to x. And here's the condition. Oh, they use mod. Well, I don't know what. I guess they both exist. Same thing. Note that weeding out lists by predicates is also called filtering. We're basically filtering. Let's write a comprehension. I don't want to see it. Let's write a comprehension that replaces each odd number greater than 10 with a bang, and each odd number that is less than 10 with a boom. Well, let's odd number that's less than 10. Wait, where's what is this again? Let's say we want a comprehension that replaces each odd number greater than 10 with bang and each odd number that's less than 10 with a boom if a number isn't odd. So we'll put that in a function so we can easily reuse it. Right, so we need a function. So we'll call it bang boom. And we're going to give it like a top number, I guess. And so let's just first make the comprehension. It will be 1 to x, I guess. Right? This is just going to give us the number. And now I feel like I want to put the if here. Condition. I mean, this is the output function, right? So I want to do, I feel like this can't be right. I could make two comprehensions, but if x, this seems stupid. Replaces each odd number greater than 10 with bang and each odd number that's less than 10 with boom. I'm not really sure. You put the guard at the end, right, but like, I want to say like x, like, what am I going to do here? We have, this doesn't make sense to me. Right. But then what is this going to do? This is just going to limit it. I want to replace it. So doesn't the replacing happen here, right? It has to happen in the output function. God, this is just going to filter it. This is giving me the numbers. So I need to put the if here, I think. So now just call the transforming function. Oh, you mean like make the function? Um, so it takes in a number. Hello. Oh my God. I think I don't understand this because how can it return a list if it's sometimes a number and sometimes a string? I think I'm not understanding this. I'm gonna just cheat and look. What are they talking about? If it's, yeah, so, okay. Oh, I thought what they were saying was it's gonna look like this. Like, I thought it's gonna say, wait, let me see. If it's less than 10, then do boom. So I thought it was gonna do boom, 2, boom, like 4. You see, like this. And that wouldn't work. What they're saying is, let's say we want a card that replaces each odd number greater than. If a number isn't odd. Oh, I didn't read this last sentence. Oh, God. I'm so bad. I didn't read the sentence. All right, so let's do this again then. So we have this goes into X. I guess like it's not a good thing to use the same letter in here. And it's odd. And then we say if X is less than, was it less than 10? Then we give it a boom, else we give it a bang. I think that works. What did I call it? Bang boom. Bang boom 10. No, 12. So this goes up to number 12, and this is like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There we go. I think that works. Yeah, I just didn't realize this last part here where we threw it out, so I got really confused how we were going to build a function that intermingles the even numbers with the odd numbers. And I just used x instead of xs. Odd returns true on odd numbers. So like, yeah, I could make. Oh, they pass in a list. That's kind of nicer. We can include several predicates. We want all numbers from 10 to 20 that are not 13. Yeah, so we can just put these in commas here. That's fine. I'm not going to test it. We can have multiple predicates in list comprehensions. We can also draw from several lists. When drawing from several list comprehensions, produce all combinations of the given list and then join them by the output function we supply. A list produced by the comprehension that draws two lists length 4 will have a length of 16. All right, so let's test this out. So if we have, oh, I see, it's going to make all the combinations. We see 2 times 8 gives you 16. Then 2 times 10 gives you 20. Then 2 times 11 gives you 22. Then we get 5 times 8 gives you 40. So it's basically going to do everything. We'll just type this in just to show it. We have 1, 4, 5, 6 because it's multiplied by 1. Then we have double of this, so it's 8, 10, 12. Then we have triple of this, which is 12, 15, 18. If I just do this, it still joins them. So it still makes it 1, 4. But then I only show the 1. So it does each one triple times. And if I show just the Y, it'll just do 4, 4, 4. Oh, no, it does it the other way. 4, 5, 6, 4, 5, 6, 4, 5, 6. It does, but it always starts with the left one first. I assume I can make a list element in here. Yep. So you actually see here what they're working on. 1, 4, 1, 5, 1, 6, 2, 4, 2, 5, 2, 6. A Tanuki cup. Yes. My partner got this for me. Do you think this is from Animal Crossing? She loves Animal Crossing, so I'm guessing it's like Nook. You think? And the other side has blah blah blah. What about a list comprehension that combines a list of adjectives and a list of nouns? All right, so let's do that. This is basically we want to make maybe a sublist here, right? So we give it adjectives like smart, silly, and sleepy. All right, we need a few tanuki. Um, what else? Cup, and we can use bear. So we have a smart tanuki, a smart cup, smart bear, silly tanuki, silly cup, silly bear, sleepy tanuki, sleepy cup, sleepy bear. Oh, they just like do the concatenation. Huh? Oh, because it's here. Smart, smart. Oops, it needs a space. Smart Tanuki, smart cup, smart bear, silly Tanuki, silly cup. Let's write our own version of length. All right, so how would you write length from a comprehension? You don't care what the value is? Plus one. I'm really bad at this. Oh, God. All right, we're going to get to monads at some point. Length, length, length. Like, I kind of want to know, like, I just want to use an accumulator and a map reduce here, you know? But, oh, we're trying to write length. So we have a 1. How am I writing this in comprehension? It's like 1. This will just give me 1 all the time. If this is 1, though, I give up. Oh, they're using sum. I thought, ah, that is just that feels like cheating. I thought there wasn't like something I could do here. So they're just turning everything into a 1 and then doing a sum on it. Yeah. I thought there was like some other way that they were going to do it. Underscore means we don't care. So yeah, it means we're not, it's like pattern matching and we don't care about it. Or it's just like, yeah. Because strings are lists, we can use list comprehensions to process and produce strings. Here's a function that takes a string and removes everything except uppercase from it. Ooh. Okay. So, um, So we're going to want to remove all the uppercase letters. So X's if element is, so we want to say not. That makes sense? Yeah, it removes the uppercase letter. Similar. Oh, I removed uppercase. Well, you know, same idea. Let's remove all the odd numbers without flattening the list. What does this mean? Right, that makes sense. You can't implement length with just list comprehension since it returns a list. Makes perfect sense. And hence why I was confused, but I didn't kind of say it that way. I should have thought it through. What are they doing here? So they have X's, so it's basically a list of lists. And they make one comprehension here. Which is taking in. So here, first we get x-axis. So what it's doing is it's pulling out the elements. So now we have just the lists. And then here for each of these, it's basically pulling out the sublist, right? Because it's saying each element from this list of lists. So now we just have a list, xs. And here it's saying I'm just going to only show even numbers. And it didn't flatten it. Looks like there's a let command. I don't know what the difference between let and just doing xxs is equal to, something. And now we're going to have our outer thing here, which is basically taking the high level, the list of lists, and it's just giving us the inside list. You can see that here. And then we're going to replace this Okay, so that was the inside here. And I think we ended up with the same results, right? Yeah. Hopefully that made sense, right? So weird to use parentheses when you already got used to looking at code using $sign. Yeah. So hopefully that made sense. This one was just pulling out the element of the list of lists. So now we just have a list, and then I replace that XS with this here. So it's taking in the excess and pulling out the actual element, but it's also checking if it's even, and then prints out the X. But that still goes back into a list, and then the outside one takes it back into its list of lists. All right. I gotta get to choir, so we'll stop right at tuples. God, that was a little rough. Oh my god, this is quite a big section on the tuples. So thanks for hanging out with me. I hope that this time I can stick through this and actually learn Haskell. I think it's a neat language. It's one of those languages like I don't know why it's neat, but we're gonna find out. Monad, 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 monad. Talk to you guys soon. I hope to be streaming a lot more frequently. See you guys. Bye.